represents perfectly what I was just describing, is that, you see this here, a random sequence of, a sequence of succession of random processes which actually describe or represent this very complex integral differential equation that describes the Lyman-alpha scattering process with absorption and scattering, etc. Right? So, yeah. And the point is, if you do this with enough photons, and you start, if you do this with enough photons, eventually the sum of all these different paths will give you proper representation of, say, the distribution of energy of Lyman-alpha throughout the scattering medium, etc., and as a function of frequency. Right, so why Monte Carlo radiative transfer? Well, I've already sort of hinted at it. This is the radiative transfer equation that we would like to solve, and I've discussed it briefly by ignoring the directional dependence of the radiation fields, right? But in practice, we cannot do this, because in practice we're interested in that radiation, in Lyman-alpha photons that we can observe, and for those Lyman-alpha photons, the scattering medium is typically not optically thick, because otherwise we wouldn't see it. Right? And in the optically thin regime, we do not expect the radiation field to be isotropic locally, right? So we should take into account, we should understand the directional dependence of the radiation field, etc. So then the problem becomes, just horrible, basically. And analytics, so you can still go and try to solve these equations, but there's only a handful of analytic solutions. And we have what I was discussing yesterday, the uniform sphere with a point source in the center. It doesn't have to be a point source, it can be an extended source as well. But if you have, say, a uniform gas sphere or a uniform slab or a uniform cube, this is when we can fully solve the radiative transfer analytically if these media are not moving, right? Once you start let them expand or contract, it's already hopeless. There's one exception, and that is a case that was discussed by Loeb and Rybicki, and I'll show you an example of that later. Loeb and Rybicki came up with an analytic solution if you have a Lyman-alpha point source sitting in a medium that is expanding along with the Hubble flow, right? A uniform medium just co-moving with the universe. The one restriction that they had is that the medium is basically has zero temperature, right? And I think actually that's fine, right? In very high redshifts, the universe would be, the IGM would likely have been cold anyway, but in any case, there is an analytic solution there. But again, that doesn't really apply to most the conditions that we're studying. So Lyman-alpha transfer consists of a succession of random operations, and so really central is drawing random variables, right? And we need to draw random variables from the emission location, we need to know the frequency, we need to know the optical depth of that the photon will travel, scattering angle, and then the components of the velocity of the atom that is scattering the photon. And each of these processes has their own complex probability distribution functions. We've discussed, for example, the scattering angle that's given by the phase function, right? The probability distribution function describing the scattering angle. The optical depth, I will come back to that. The components of the velocity components of the atom that is scattering, those are actually quite messy, and I will not actually show these, but I'll just mention again that they are messy. Right? So very central. Let us start very simple in a very simple way. So how do we draw random variables in general? Right? If we have some variable x that obeys some probability distribution px. Right? We know that this probability distribution must be normalized. Right? So what we do then is we draw random numbers between 0 and 1 and invert basically this equation. Right? And you can understand that if nr is, for example, very close to n1, your x would be at the very tail end of your probability distribution. If r is 0, you would be very much, well, I guess near the beginning of your probability distribution function. It's a bit simple terms, but the main point is that if you invert this equation, then it turns out that your x, the randomly generated x, follows a distribution that closely matches your probability distribution function, right? So this is an example, a Gaussian with standard deviation 1, right? And this is 100 random draws from that Gaussian distribution. It doesn't look doesn't look that good yet. If you do 1,000, it looks like this. If you do 10,000, it looks like this. And if you do 100,000, it looks like this. Right? So that's just inverting this equation that I was showing you. Right? The nice thing, of course, about this Gaussian is that you can analytically invert it. Right? So that's nice. So then you can actually, this equation is just, well, you can invert it and you can write down an expression for x once you have generated r. So it's very simple. However, in general, our distribution functions cannot be inverted at all. Right? And when that is the case, you generally apply this thing called the rejection method, or that's one of the ways you can do it. This is the way we do it. Right? I think this is a very efficient way of generating or drawing variables from probability distribution functions that are not invertible very easily at all, or not invertible at all analytically. Right? So this is px again, a random, I've just drawn something by hand here. What we usually do then is you draw some other distribution function t of x, which lies everywhere above px, but which has a much simpler form and such that we can actually invert it analytically. Now, because we know that px is normalized to 1, and because tx is larger than px everywhere, we know that this function is not normalized anymore, but that's fine. Right? We can still draw random numbers from this tx by just inverting tx, and we can analytically do that. Fine, right? So let's start with that. Suppose we draw a random variable from tx, like we did for the Gaussian case. This is just one draw, and suppose we land here at x1. And what we do then is say, okay, I'm going to just compare. I'm going to compare the function of my newly introduced function, evaluated at this value of x1. And compare to the value of the true underlying probability distribution function. Right? And I call that ratio y. And then I'm just going to draw another random number, and if that number lies, basically, if that number is less than y, so in a normalized sense, if that number lies below this px curve here, then I accept it. Right? So the step, I think if you want to prove that this works, it's actually, it's really, the proof is actually pretty, I think it's ugly and I don't even want to show it. Instead what I'll show is, I've just taken the Gaussian that I showed before and I just cut something off it, right? And I think I just put some strange exponential to make sure that I could not analytically invert this function, right? So this is just a PDF that I had before, but I cut a piece off, right? And as a result, I had to renormalize p of x a little bit, right? Because the original Gaussian peaked at about 0.4. This function has now something cut off here, so to renormalize, the peak lies a bit higher. This you cannot invert, but if you apply exactly the steps that I outlined previously, so this is just a visual proof, then you get this, right? So it works really nicely. Oh yeah, and I call this the wave, but I think it could also be the Lyman-alpha profile, right? With poor, if I understand Matthew, with poor spectral resolution, basically. So. The rejection method applied, it should read. In any case, the point is that there is a very, very simple three-step approach to generating random variables from arbitrary probability distribution, and that's very useful for Lyman-alpha because most of these probability distribution functions we cannot invert at all. The first one is, for example, the emissivity profile, which can take on any value, right? So. Suppose you have some arbitrary gas distribution given by gas distribution. That gas distribution can emit Lyman-alpha photons either through recombination, collisional excitation. So this will give us a complex emissivity profile, which is given by this J nu R. Right? R is a 3D vector, can be 1D as well, if you're spherically symmetric. But you can convert this emissivity profile into a 3D distribution function by just normalizing by the total, right? So then you get a 3D probability distribution function, and if you want to select a random site where the Lyman-alpha photon is emitted, you just apply this rejection method that I outlined earlier to this function P of R. Second thing you would do is you like to pick a random frequency. We pick that from the void function. Now, void function cannot be inverted either, at least I can't, analytically. So that's, again, we apply the rejection method. And you pick a random direction, right? And that you can just pick any arbitrary direction when you emit it. Now then you know that photons typically when they travel a distance e to the minus tau, right? That's the very definition of optical depth, right? This comes from the radiative transfer equation. This is how we defined optical depth, right? So we draw this tau from this exponential distribution that we can invert analytically. Now once we know tau, right, then we can actually convert it into a physical distance by checking, stepping through your scattering medium and seeing like at each step how much additional opacity do I add, right? So you generally numerically solve this, right? So in each step you have a number density of hydrogen atoms, and then you check locally what the gas is doing, at what frequency, what velocity it has, because the local gas velocity will modify the apparent frequency of the photon in the frame of that gas. Right? So you're stepping through your gas, making sure you Doppler boost in the frame of the gas at each step, and you evaluate tau. And once you reach the randomly generated tau, you basically stop, and you have displaced the photon by a distance s. Right? The new position would then be given by r prime would be r plus s times the emission direction. Right? Now this is step 3. I'm not going to write out, but step 3 is, I think, the messy part. Right? So you would like to know which atom is basically scattering the photon. Right? That's I think one of the messy parts. Generally speaking, you know that the velocity distribution of atoms is given by a Maxwellian, right? So you say, well, why not pick just pick them from a Maxwellian distribution? Well, the problem is that, if your photon has your photon is moving with some frequency in this direction, if your atom is moving this way or this way, in the frame of the atom, the photon will have very different frequencies, right? And because the frequency, the cross-section is so strongly frequency dependent, the scattering probability can strongly depend on the velocity of the atom along the motion of the photon, basically, along the propagation direction of the photon, right? So this is the one thing I think you have to, it requires a bit of work. But again, if you have the rejection method, it's really, once you supply the probability distribution function of your atom, the velocity of your atom, you're done, right? Because the rejection method will take care of it. So once we specified the atom, then we need to choose the direction in which the photon gets scattered, and that we draw from this phase function. Right? It can be dipole or isotropic, or for Lyman-alpha, it's typically something in between. And at the end of the lecture, I'll actually I'll make a little bit clearer why I'm not so specific about the functional form of this phase function, why I have been deliberately a bit vague about this. I think that will become apparent on the very last slide. That's going to be a bomb, it's going to surprise you so much. I think you, for coffee, you won't know what to talk about. And in any case, so just to increase the expectation levels. So then, once you've done that, you have a photon again propagating in some direction with some, right? Once we've specified the atom's velocity and the outgoing direction, the frequency of the outgoing photon after scattering is fixed, right? We don't need to do that. That comes out naturally. So now we have a photon again propagating in some new direction k out with a new frequency x, and we basically go back to step 2. We just generate a new tau, see what happens, and we just repeat this until the photon escapes from the scattering medium. Right? And remember, we do this for each photon. Right? So you do this enough times, then you should be okay. Now the thing is, this procedure is, well, I know that this procedure is prone to bugs. Right? So you would like to test it in as many ways as possible. So the first thing you should test if you do this is to compare with analytic solutions for spectra that people have computed, right? I mentioned that we have analytic solutions for spectra emerging from, say, static spheres or static slabs or static cubes. This is the first thing you would like to test. Whether the energy, the spectra of the photons that come from your Monte Carlo actually agree with these analytic solutions. Now in this case, these colored lines are actually histograms constructed from Monte Carlo methods, and these dashed lines are analytic solutions. Right, and here you sort of see that, especially if you go to very high optical depth. I've shown this before, but if you go to very high optical depth, in principle, the analytic solution should almost provide a perfect fit to your to the full radiative transfer. Right? On smaller optical depth, you see it doesn't quite. Right, there's some mismatch here. Maybe it's not that bad, but in any case, it shouldn't be that good as you decrease the optical depth. But the interesting thing about this is that in the previous lectures, when I was talking about this particular solution, I was saying like how, well, these analytic solutions are derived basically under the assumptions that you're scattering in the wing. Right? So this makes very specific approximations in the radiative transfer. Basically, you're only wing scattering basically was the approximation in the analytic solution. So the good agreement between analytic and Monte Carlo basically means that you're not testing resonant or core scattering at all, right? And that's kind of interesting because for two reasons. The first reason is that resonant scattering or core scatterings account for the vast majority of events in your Monte Carlo, right? Remember that optical depth 10 to the 7, you scatter about 10 to the 7 times in a static medium, 10 million times, right? But the number of scattering events that actually mattered was only a few hundred, right? So there is the vast majority of those 10 million scattering events actually do not matter, right? And you're not even testing those scattering events with this when you have this kind of test. The other thing is that and I'll come back to that later, you could actually just skip these 10 million scattering events, well, not all of them, but you can skip the vast majority of them and speed up the code tremendously, right? And we'll talk about that in a second. So what you would like to do too is, I mentioned, once you generate a new direction, an outgoing direction of your photon, once you've generated the velocities atoms, you basically get the outgoing frequency for free, right? So it would be interesting to check the redistribution functions R, right here it's Q, but it's actually what I called R before, the analytic expressions for the redistribution functions, and compare these to the ones that you get from the Monte Carlo. Right? These are testing core scattering, and so now you're testing things that you would not test with a Neufeld test. Right? And again, it works. It should work remarkably well. These expressions should be very close or should be in perfect agreement basically with the analytic solutions. In this case, because here for the analytic solutions there's no approximations involved either. Right? I showed this as well. The number of scattering events is sort of another way to test resonance core scattering, right? Because if you have the core scattering correct, we sort of know then how many core scattering events are required to be boosted to a frequency where you can escape, right? And this is something that Adams derived in early 70s, and in the Monte Carlo code you can test and it works. Right? So the thing is, I don't think, this test I'm not entirely, if I didn't know beforehand that that Adams' solution was so accurate, I would not necessarily consider this a test, right? It would more be a verification of this intuitive argument that Adams provided. But I think it's still, now I think it's kind of now that it agrees, I think it is a nice test. Most tests would be interesting, like in general you're interested in scattering through moving media. I think what we learned from Matt's talk yesterday and today is that the gas kinematics is one of the things that is driving Lyman-alpha escape strongly, right? And also turbulent motions. So we'd like to understand if our code properly accounts for bulk motions in the gas and properly deals with this. Right? So this is the Rybicki-Loeb solution in green, right, for the spectrum. And here the spectrum has these weird units of x hat, which relates to my ordinary frequency units in a bit of a strange way. It doesn't really matter right now. The only thing that matters is that the Rybicki-Loeb solution is in green, and the Monte Carlo solution is again as the histogram. So this kind of thing would test whether your code is actually working once you have gas motions present in the gas, right? And maybe I should just explain. Now this is the Rybicki-Loeb solution. X hat has an inverted sign compared to our original definition, right? So large values of x hat corresponds to very negative values of x, which in my case corresponds to reduced frequencies. Right? So this is actually a highly redshifted spectrum. And that's not surprising because this is a solution in which we have Lyman-alpha photons scattering through an expanding optically thick medium. Right? So the spectrum should be redshifted. Right. So I already was hinting at this. The fact that Lyman-alpha spectra from optically thick media are generally very insensitive to core scattering. Right? So the fact that spectra emerging from optically thick media are so insensitive to core scattering gives us an opportunity to actually speed up the code. And I'm somewhat embarrassed to admit it, but when I was developing my code as a student, I was reproducing these perfect solutions, and I was doing it really fast, right? And I was doing it with a number of scattering events that was 1,000 times less or 10,000 times less than what was expected based on Adam's arguments, right? So I was really surprised. It should have taken like 1 million scattering events per photon to escape, and they came out after 1,000, and it looked perfect, right? So I really thought that there was a mistake in Adam's analysis for actually a few weeks. You know, I was trying to figure it out, couldn't find it, and yeah, it turned out there was a bug in my code for core scattering, which sort of forced my photons into the wing by mistake, you know. But once they're in the wing, it was fine, because the wing scattering part was working just fine. And suddenly it was like, this is, you know, because there was, I'm giving the proper reference here, sorry, I would like to give the proper shout out to Ahn et al., who in 2002, I give the proper reference later. They already mentioned in their paper that there was a way to speed up the code, but I couldn't, you know, when I was reading the paper, it wasn't really clear to me how it was done. But suddenly, you know, with this bug in the code, I was like, that's what they mean. You know, I can just force these photons into the wing, and, you know, everything is going to be much faster. And that's basically what you do when you do accelerated Monte Carlo. Right, so I've mentioned this as well, now just the numbers. Number of scattering event goes as tau. Peak frequency is about 12 for an optical depth of 10 to the 7. So the number of scattering events, which goes as x squared, and the number of scattering events in the wing where you escape goes as x squared. So that's about 150. So you have 150 scattering events that matter for the escape in the end, and that's 5 orders of magnitude less than the total number of scattering events that you have in the system, right? So the key is to accelerated Lyman-alpha transfers to skip these unnecessary core scattering events. But this is, of course, it's not trivial how to do this. Right, so the question is, if you have a Lyman-alpha photon that is close to the line core, right, to sort of force it into the wing. So you have 2 questions. How close do I mean? And the second question is, like, how do I, well let's just focus on the first one. So how close? So typically how close you are, or you can be, or you can sort of start pushing photons away, is given by this critical frequency, right? X crit. So the idea is that if a photon if nature, which is always pushing photons back to the line center, once it gets pushed back in this region, given if it's X crit Doppler units away from line center, we basically force it back out. And the larger you pick this value, of course, the more events you skip and the faster the code is. And of course, you should be a bit careful because it also increases the potential for inaccuracies in the calculation. Now, so what we usually do is then we force it to the wing by forcing an encounter with a fast-moving atom. And I think, to be fair, I don't think it even matters that much how you do this, right? You can even brute force it into the wing by just literally put it in the wing at some value and just let it go. But I think the standard way, I haven't tested that carefully yet. I think, the Neufeld test and other things definitely work with such a simple approach. But the way it's usually done is you sort of draw the velocity distribution from a truncated Maxwell-Boltzmann distribution. So you say, I'm going to ignore all photons that are moving very slow, and whatever, of course you have to make some quantitative statements here as well, but the idea is, again, you truncate the Boltzmann distribution and you only focus on those atoms that are in the very far wings of the Maxwell-Boltzmann distribution, and you let those photons scatter. Right? And typically speaking, you reduce the number of scattering events by 2 or 3 orders of magnitude when you do this. Right? So it makes a tremendous difference in practice. But you always have to be careful, and I think especially when you have large velocity and density gradients. So for example, in these multi-phase ISM calculations, these Neufeld models, there you have very large density gradients, right? You have these dense clumps with a very sharp surface. There you have to be somewhat careful with how you choose your acceleration scheme. And a lot of people have worked on this and have tried to explore ways to optimally accelerate codes. And usually I think one way to do it is have sort of a dynamic system which determines the precise level of acceleration depends on the optical depth of the cell in which you're scattering, right? And so that's one way to do this. And when I'm going to talk about polarization, this is something where you have to be a bit careful that you're not skipping over scattering events that affect the polarization. Now there's one, I think, subtle thing that I'll briefly talk about before moving on to polarization, and that is, generally speaking, if you have like a random gas distribution and you're following your Lyman-alpha photons through it as they're scattering, it's actually not entirely trivial to get observables from this. And the idea is that you're simulating Lyman-alpha transfer in a source that is a cosmological distance away, right? So ideally you would like to simulate, when we're observing those photons that actually came all the way from 10 to the 30 centimeters away and landed exactly in our telescope, right? So you would like to ideally you would want to model that process. You would want to model the escape of those photons that escaped and in the direction of the telescope exactly, right? Otherwise we wouldn't see them. Right. Now, of course, in practice, this never happens when you do Monte Carlo. Your photons escape. They escape over in all kinds of directions, and effectively, you're looking at, when you do Monte Carlo, you're looking at your simulated source from n different angles, right? And the angular resolution, or the precise. Well, let me get back to this in a second. You're looking at it from n angles. Right. So what are we going to do? Like, how do you construct these images? Like, how do you make sure that you're actually representing an observation, basically? And it's interesting that, this problem is a problem that Ulam and Metropolis struggled with when they were doing their experiments for the neutron capture in these different media. And I remember when I was at MPA, I found a book on Monte Carlo methods, and it was interesting. One of them was actually on this neutron capture process. And it's interesting that some of these sections that were discussing this particular aspect of the problem were classified, so I couldn't read it. So that didn't help, but in any case, right. Oh, so one thing you can do is say, okay, what I'm going to do is when my photons escape from the simulation or from the simulation domain, I'm just going to collect only those photons that escape within some sort of, within a finite solid angle centered on some pre-specified direction. And that makes sense, that should be okay. So that makes, yes, the problem is, of course, if you pick your d omega small, you're losing a lot of information. And in fact, you're losing d omega over 4 pi of the photons that you were using. The rest you can just throw away because they're not relevant observationally. Right? So that's not a very efficient way to extract information from your Monte Carlo simulation. And of course, also you can say, well, then I make my d omega large. But effectively, what you're doing is you're observing your source from averaged over a whole range of angles, right? So you're really like, if there's sharp features in your spectra, in your source, in your image, you're washing out over them by averaging over many viewing angles. Right? So there's so I think this is, you lose information and also you're smearing out your images, you're blurring them in this kind of methods. Now the second solution, which I think which is the one that is the appropriate one, well, the one that was classified. Well, it's not really classified, of course, but I think this was the method that was invented then by Ulam and Metropolis. And this is known as this next event estimator or peeling algorithm, right? So what you do in this way is, it's actually pretty bizarre. So remember, I have this random path of Lyman-alpha photons bouncing around through a simulation. For each scattering event, what you say is each scattering event corresponds to a single point source, and I'm just going to compute the apparent brightness of that point source, right? And you're going to repeat that for each scattering event, for each photon. Right? So that's strange. I mean, you have, say, n photons that represent some, say, 10 to the 42 ergs per second. So then each photon carries an apparent luminosity of 10 to the 42 over n ergs per second. And you let each photon, just that single photon that carries that much energy, you let it contribute n scattering events. You do that calculation n scattering events times for each photon. And it's kind of, in the end, it turns out, and that's, I guess, the proof that is sort of classified, it does converge to the proper solution. And I think the advantage of this method is that you don't lose information. You know, unlike the case where you sort of bin up your photons into a finite solid angle. I mean, the problem is that this can be, especially when you parallelize your codes, this can be quite computationally demanding. Right? You can imagine that if you have to do this for each scattering event, calculate the escape probability in that direction, etc. It can be problematic. Right, but I just want to show you one application of what this may look like. This peeling algorithm, like you get razor sharp images. This is an idealized case in which you have a Lyman-alpha source surrounded by 6 clumps. So this is a Neufeld model, but highly idealized. Right, you have your clumps. I'm going to assume the clumps are optically thin, and the reason for that is then you can do more analytic calculations. And your Lyman-alpha source is just emitting photons, and these photons escape, so this would be a point source. Right, I'm going to ignore the point source of those photons that do not escape. I'm just going to focus on the scattered radiation. So the scattered radiation should only come from these spheres. Right? So if you apply this next event algorithm, you get like razor sharp images basically when viewed from all directions. Right? And just to zoom in a little bit on this, zoom in on this top image here. Right, you see, this blurring is entirely due to the pixelation of the image. Right, but Lyman-alpha source sitting here is illuminating the cloud from below, right? And you see the histogram of the intensity scattered radiation when you make a slice through this here. The red line is analytic, what you would expect analytically, right? So this makes the images as sharp as you could possibly get it. If you were to sort of average your photons over viewing angles, you would blur this out. Oh, right, I don't know if you noticed this. So can you see this actually? No, I think you could, no? Sorry? Then never mind then. I think we'll discuss it over coffee. How much time do I have? 10. Excellent.
It was on mute.
You know what? It was on mute.
Yeah.
You might as well just, it's big. Just let you stare at this picture while I set up again. I think the longer you stare slowly, this is actually a pretty sophisticated simulation, but the longer you stare, you see something. Anyway, it involves a wand and Hermione and Harry and others. But in any case, so we know now that Lyman-alpha is typically more spatially extended than UV continuum. Right? I mentioned yesterday how we currently do not understand well yet what the origin is of the spatially extended Lyman-alpha radiation that we see, whether it was produced in situ. If so, what was producing it in situ, or if it was scattered, right? So now the interesting thing, of course, scattered radiation can be polarized, so there is some information in there. So I've shown you this picture before. It's again an electromagnetic wave incident on a free electron. The electric vector of the electromagnetic wave starts to make the electron oscillate along the electric vector, and that acceleration then gives rise to re-radiation and scattering. Right? The next slide, from now on, I'm going to drop the magnetic field. So I'm going to again show the propagation direction of the radiation with, with the black line. And radiation has only one vector associated with it, the electric field. But I'm going to decompose it into 2 components. So just to emphasize, I don't want to confuse you. From now on, this is the radiation propagating in this direction. This is the electric vector alone. Right? simplified representation of this process. So now let's say the incoming radiation lies in the whiteboard, right, or it lies on the screen. It's just coming in like this, and let's say the radiation is scattered by 90 degrees, so straight into the room, into the projector. Now we know that suppose that the electric vector of this incoming radiation is perpendicular to the direction of the incoming photon, right? So it's oscillating in the board, but perpendicular to the incoming direction. Right? So the electron starts oscillating in this way, and now suppose the radiation gets re-emitted in this direction. We know that the observer, the projector, basically sees the full oscillation of the electron and basically experiences the full re-radiated emission, right, that we talked about earlier. Now suppose I rotate the electric vector by 90 degrees such that it's pointing into the room. Right? In this case, the projector doesn't see the motion of the electron at all. Right? So as a result, the scattered radiation in this direction will be 0. And generally speaking, for unpolarized radiation, the electric vector can take on any value. Right? So what this process actually does, what this scattering by 90 degrees of this free electron only transmit this particular component of the electric vector of the radiation. And if you think about it, incoming direction is this way, outgoing direction is this way. The plane of scattering, the plane of scattering is parallel to this stage here, right? That's the plane of the scattering. It's parallel to the stage here, right? So one thing you can say is that if the component of the electric vector that lies in this plane here, right, that basically gets destroyed by this 90-degree scattering process, while the electric field vector that was perpendicular to this scattering plane got transmitted fully. Right? So just to draw this a bit more. So here I have the scattering plane, so what was previously perpendicular to the stage here in green. Right, what that does is I have my incoming photon coming in like this. The electric vector is pointing in this case in this direction here, it's not drawn. There's two components to this electric vector, one that lies in this plane and one that lies perpendicular to the plane. The scattering leaves alone this component perpendicular to the plane, just as I showed before. Right? However, the component that lies within the plane, that actually gets suppressed. And how much it gets suppressed depends on the angle. The example that I just showed had 90-degree scattering, so this component was gone. Right? So this component was sort of suppressed by a factor that goes as cosine theta. Right? When theta is 90 degrees, this component is 0. And now, when we talk about polarized intensities, you can sort of define these two intensities. One of them, the intensity associated with the electric vector inside the scattering plane, and one of them perpendicular. Right? And clearly, the total intensity is just the sum of these two components. Right? So just, and just to stress that, so the different impact of scattering on these two, so scattering sort of affects these two different intensities, I parallel and I perpendicular, in different ways, and in ways that depends on scattering angle. So the difference is maximum when this scattering angle is 90 degrees, right? This is when you really kill off one of these components and transmit the other one completely. Right? And that's, so large scattering event, large scattering angle, large polarizations. So what this may look like on the sky, and this is from I think an opinion piece on Matthew's observations in nature. So what you see is, suppose you have a point source sitting here emitting Lyman-alpha photons. If these photons scatter at large impact parameters, so far away from the source, they have to scatter by angles that are close to 90 degrees. Right? And in this case, we know that the polarization properties of the scattering by the free electron are maximized. Right? So you get very strong polarization very far away from the source. If you look very close to the galaxy, you typically get scattering by very, well, if you call this the scattering angle here, by very small angles. So the scattering-induced polarization is actually much smaller. Right? So as you move closer to the galaxy, you see the polarization decreasing. Right, so these are observations, actual observations of the process from Matthew's paper. So the idea here is that, I don't know how hard it is to see actually, but the idea is that the intensity corresponds to the intensity of Lyman-alpha emission. You sort of see the linear polarization, these polarization vectors which sort of measure basically the excess of the intensity in one of these electric intensities over the other, right? So it sort of measures the preferred orientation of the electric vectors along the source when viewed on the sky. And so you see these polarization vectors form these concentric arcs, just as in this cartoon that I showed you earlier. And so that sort of provides evidence for the scattering interpretation in this kind of observation, right? Which is, was a first basically. Before that we didn't really know for sure how much scattering was contributing to these kind of spatially extended sources. Right? Now, okay, what do I want to say? Right. I just want to make like one quick analogy. So this was all for a free electron, right? Why the situation is a bit different for Lyman-alpha. So to make the analogy what we talked about earlier, right? Before I was always talking about intensity or the intensity of the radiation in terms of a total, right? And when we were talking about scattering angles, we were talking about a phase function, right? It just gave us the ratio of the intensity of the incoming and outgoing direction at some angle. Right? But when you talk about polarized intensities, you have two different intensities, right? So you do not have a phase function anymore. Instead, you need what is known as a scattering matrix, right? Because you now have two components to your intensity rather than one. Now the interesting thing is that, I'm just going to give you the expressions because there's no time. The scattering matrix for dipole scattering takes on this form. The scattering matrix for isotropic scattering takes on this form. And this is completely, say, the 2D analogy of what we talked about earlier in terms of phase functions, right? We had a phase function of this form for dipole scattering. We had a phase function of this form for isotropic scattering. This is just a 2D analogy of these phase functions that we discussed earlier. Now, I said before that Lyman-alpha scattering was sort of a superposition of this one and this one. Now, that's the case, I mentioned that. So this is actually what's really happening. So it's a superposition is actually done in this 2D representation. Right, so the scattering matrix of Lyman-alpha scattering is given by this expression here. So you basically have one parameter that gives the relative weight of each component. Right? How much is dipole scattering, how much is isotropic scattering. Right? And E2 is just 1 minus E1, right? So there's only one parameter that determines the weight of these two. Now pure dipole scattering would have E1 as 1, so that's the case I was just discussing when we were looking at this free electron and the response to an incoming electromagnetic wave. Isotropic scattering as E1 is 0, right? So this term goes away and we're left with this matrix here. That basically says, like, it doesn't matter where the radiation come from, which way it was polarized. It's going to be scattered in arbitrary directions with arbitrary polarization. Right? And Lyman-alpha should be somewhere in between, right? So let me now actually show you what E1 looks like for Lyman-alpha. And it's pretty bizarre. This is what it looks like. So remember, this is pure dipole scattering. This is isotropic scattering. So Lyman-alpha actually, this is the Lyman-alpha resonance here. And what X already showed us is that Lyman-alpha resonance is actually Lyman-alpha is not a single line. It's, there's fine structure splitting in the line. And usually people call the two different components H and K. Very close together. For us, it generally really doesn't matter. But suppose you were to go to scatter through your H line, for example. For the H line, it's actually perfect. It turns out to be, so that's this particular transition. It's the exact half isotropic and half dipole scattering. K scattering through this particular transition, if you look at this line closely, here, right here, E1 is 0. So it's perfectly isotropic scattering once you go through this particular transition. So the hydrogen atom behaves, when you K scatter, it behaves like a perfectly spherical, well, it doesn't care at all about the incoming direction, the incoming polarization. And it turns out the reason for this, that the 2p half state doesn't care at all or behaves like a perfectly isotropic scatterer, is that if you look at the wave function of the 2p half, the quantum mechanical wave function of the 2p half state, it's actually perfectly spherical. Right? So it's almost like when the atom goes into this state, it instantly lost memory of the direction and polarization of the incoming photon. right? And it's kind of funny, like when I wanted to show you actually what this wave function looked like, and I always had a hard time finding, like in textbooks or something, the functional form of this. I found it in a book from 1934 by White when I was at CFA. It was in the library there somewhere, and I had a very bad scan of it in one of my presentations, so I decided not to show it this time because it was not nearly it didn't look nearly as nice as Gandalf, for example, so I decided not to show it. But I think we're focusing on, I think in this sense, have been just explaining K and H, what's happening, but the most obvious thing that I'm not mentioning is the bizarre shape of this thing, right? This E1 goes negative, right? So I'm not even sure what that means, right? It's like the weight of dipole scattering goes negative. In practice, the reason I'm not so worried about that is in practice this doesn't really matter, right? Because this is a very narrow range of frequencies, and precisely at what energy you actually absorb is also modulated by the velocity of the atoms, right? So scattering events here, for example, where this weighting is negative, occur very rarely in real gas. What is much more crazy about this plot is that this thing once you go away from resonant, it quickly shoots up to 1, right? That's what is truly bizarre about this, because we talked in the first few lectures, I was always mentioning these wave functions, how when Lyman-alpha excites hydrogen atoms, the wave function sort of change into this double-lobed 2p state, right? The electron is confined to the orbit set by this quantum mechanical wave function. Now apparently once you scatter away from resonance, suddenly the electron starts acting like a free electron again. Right? It's E1 goes to 1, that's pure dipole scattering. That's exactly the case that I was describing. The radiation is coming in. If the electric vector is pointing this way, the electron will oscillate in perfect alignment with the incoming electric field. Right? So, I don't know, I've had a beautiful sentence about it, I thought. So here it comes. For wing scattering, quantum interference releases the electron from the boundary set by the wave function, and it behaves as if it were truly free. Done.